Alright, welcome back everyone. This is the second half of things. We're going to be going through metabolomics here. And this is just big, fancy, old terminology for the study of metabolites, determining their presence and how much of them actually exists in the system. Now in your slides, there were two main methods that were discussed. The first one being mass spectrometry, and the second being NMR, or nuclear magnetic resonance. So in mass spectrometry, I saw two main words. I saw LCMS and I spotted GCMS as well. Now before we sort of start with things, I think it's important to give you a small reminder on what these two are. In LCMS, or liquid chromatography mass spectrometry, what you're trying to do is you're trying to separate the sample first using chromatography. If you use liquid chromatography, then it would count as LCMS. If you use gas chromatography, it would count as GCMS. Okay, so just putting that out there in a sense. Okay, in this video we will go over what every mechanism is, or what every methodology is all about. So just a small short definition, how it works, or the steps you need to take in order to get your final result, a clinical application for each, and then finally just how you can interpret results if you need to, in a sense. Like, it's all going to be within the limits of what I heard in the recording and what I saw in the lectures. Hopefully this will be a short video. I know you have quite a number of things to do with the finals and everything coming up, so I'm making all my videos 6 minutes maximum. Okay. Alright, we shall begin. So whilst this is a more complicated way of doing things, this whole metabolomics things, and it utilizes those big fancy names like mass spectrometry and NMR, instead of just doing things like the regular old guy with colors, it's quite simple. For example, in mass spectrometry, whether it's liquid chromatography or not, all you need to do is you get things through the machine, and that is after separating them by liquid chromatography or gas chromatography. You're going to detect them using a mass spectrometer, and then you're finally going to sequence them using something called fragmentation. Now, if you're familiar with mass spectrometry and how it works, then this will not sound new to you. So after fragmentation, you're going to take those fragments and use them to measure a certain amount of whatever substance you're looking for. So for example, if we're trying to measure how much creatinine we have in the system, and we've gone through this 3 steps, that is, one being separation by either LCMS or GCMS, just putting that down there, and then 2 being passing them through the actual mass spectrometer, and then 3 being fragmentation, you're going to end up with a nice graph looking thing. Again, if you're familiar with the way mass spectrometry works, this won't look very unfamiliar. This is all about mass and charge and whatnot. So what it's going to do, what a mass spectrometer would do, is give you like those different lines or peaks in a sense, and depending on the mass that the substance you're looking for has, you would be able to tell how much of it is in the system based on these peaks. So after purifying creatinine, putting it through the machine, running it through the detector, finding the different peaks, whether it be small, big, or large, you get those results that sort of give you this idea about things. And a good word to use for this entire process would be quantification. So what you're doing is you're trying to quantify how much of a substance is there. Now this is much better than using color to know, color intensity and whatnot, like in the previous video, because if something is up with the reaction, then it's fine. There is no effect on the final results, and that makes it more reliable than using targeted clinical chemistry in a sense. If you think about it, if something went wrong with picric acid in the previous video and there wasn't enough of it, then you wouldn't get the substrate that was colorful, right? So you wouldn't get the Janowski complex, and that would just mean trouble. You would get into this whole loop of troubleshooting and you would probably not get out. So in a sense, that sort of explains why mass spectrometry is much more preferred. I just thought of putting that out there, even though it's not in the list. Let's get back to the list and make sure this video doesn't go over 6 minutes. So this is the what part is probably complete for both of them. The how part is complete for mass spectrometry, but we didn't go over nuclear magnetic resonance yet. The clinical part, I would consider it done for mass spectrometry because of the example I gave you, creatinine. We already know why creatinine is important to measure. If not, get back to the previous video. And finally, results. There wasn't much emphasis on figuring out how you should read a mass spectrometer, so I am not going to get in there. Okay, now we get to nuclear magnetic resonance. Let's first just get rid of this stuff. So, NMR, the fancy old name. Again, what you're going to do, you're going to get your substance, you're going to place it in a vial, and you're going to, of course, after purifying it and whatnot, you're going to get it in this big old machine. And after you put it in that big old machine, you're going to get a spectrum. And your spectrum is going to be not based on mass, but based on structure. Do you need to know how this machine works? Well, I've gone through your slides, I've gone through your recordings. I did not hear anything about that, so I am not going to talk about it. Again, what sort of results would you expect? You're going to get peaks, you're going to get small peaks, you're going to get big peaks, large peaks, just like in mass spectrometry. And every peak would again represent a metabolite, just like in mass spectrometry. And depending on the levels, you can diagnose a disease and then move on to treatment and so on, just like in mass spectrometry. So that was very short. One thing I should talk about, but I didn't talk about yet, is probably this idea of metabolic flux analysis. Now, there are a lot of fancy big words in medicine, and this is just another one of them. This is just fancy terminology for finding out information about how fast levels of something are changing. So if something is decreasing in amount, how fast is that decrease? What is the rate? If something is increasing in amount in that specific body, then how fast is it increasing? What sort of rate are we looking at? So in our case, let's take our example again, creatinine. If there is a large increase in creatinine in a small amount of time, we would say that there was a high rate, and that would be the result that you would sort of correlate with this huge big fancy term, metabolic flux analysis. Let me give you another example. Alcohol phosphatase. If you look at, if you do this whole metabolic flux analysis for this substance, and you look at its rate of change in the body, it can tell you about the person's liver condition. So like I said, it's all about two things. One being diagnosing a disease, and then the other one being moving on to treatment and so on. So in general, this is a very, an outline in a sense. There are many more details in your lectures, but I hope that this video can give you that sort of push to be able to dive deep into all the other details. This is probably not above 6 minutes. I am glad, and I will probably just close this thing just for the sake of keeping my word.